Welcome friends. In the previous session we have introduced with binary relations and ways of representing relations. In this session we discuss various types of relations. Types of relations. Consider a given set A. Important types of relations which are defined on A are reflexive relation. A relation R on a set A is reflexive if A related to A for every A belongs to A. That is if ordered where AA belongs to R for every A belongs to A. Symmetric relation. A relation R on a set A is symmetric if whenever A related to B then B related to A. That is if whenever ordered pair AB belongs to R then ordered pair BA belongs to R. Antisymmetric relation. A relation R on a set A is antisymmetric if whenever A related to B and B related to A then A is equal to B. That is if whenever ordered pair AB belongs to R and ordered pair BA belongs to R then A is equal to B. Transitive relation. A relation R on a set A is transitive if whenever A related to B and B related to C then A related to C. That is if whenever ordered pair AB and ordered pair BC belongs to R then ordered pair AC belongs to R. From the above definition the following lemma is easily obtained. Lemma: a relation R on a set A is not reflexive if there exists A belongs to A such that ordered pair AA does not belong to R. A relation R on a set A is not symmetric if there exists ordered pair AB belongs to R such that ordered pair BA does not belong to R. A relation R on a set A is not antisymmetric if there exists distinct elements A and B belongs to A such that ordered pair AB and ordered pair BA belong to R. A relation R on a set A is not transitive if there exists ordered pair AB and ordered pair BC in R such that ordered pair AC does not belong to R. Example 1. Consider the following 5 relations on the set A consisting of 1, 2, 3 and 4. R1 is the set consisting of the ordered pairs ordered pair 1, 1, ordered pair 1, 2, ordered pair 2, 3, ordered pair 1, 3 and ordered pair 4, 4. R2 is the set consisting of the ordered pairs ordered pair 1, 1, ordered pair 1, 2, ordered pair 2, 1, ordered pair 2, 2, ordered pair 3, 3 and ordered pair 4, 4. R3 is the set consisting of the ordered pairs ordered pair 1, 3 and ordered pair 2, 1. R4 is equal to 5 the empty relation. R5 is equal to A cross A the universal relation. Determine which of the relations are A reflexive, B symmetric, C antisymmetric, D transitive. Solution. A. Since A contains the 4 elements 1, 2, 3 and 4, a relation R on A is reflexive if it contains the 4 pairs ordered pair 1, 1, ordered pair 2, 2, ordered pair 3, 3 and ordered pair 4, 4. Thus only R2 and the universal relation R5 are reflexive. Note that R1, R3, R4 are not reflexive since, for example, ordered pair 2, 2 does not belong to any of them. B. R1 is not symmetric since ordered pair 1, 2 belongs to R1 but ordered pair 2, 1 does not belong to R1. R3 is not symmetric since ordered pair 1, 3 belongs to R3 but ordered pair 3, 1 does not belong to R3. The other relations are symmetric. C. R2 is not antisymmetric since ordered pair 1, 2 and ordered pair 2, 1 belong to R2 but 1 not equal to 2. Similarly, the universal relation R5 is not antisymmetric. All the other relations are antisymmetric. D. The relation R3 is not transitive since ordered pair 2, 1 and ordered pair 1, 3 belongs to R3 but ordered pair 2, 3 does not belong to R3. All the other relations are transitive. Remarks. The properties of being symmetric and antisymmetric are not negatives of each other. For example, the relation R, the set consisting of the ordered pairs ordered pair 1, 3, ordered pair 3, 1 and ordered pair 2, 3 on the set A consisting of 1, 2 and 3 is neither symmetric nor antisymmetric. On the other hand, the relation R1 which is the set consisting of the ordered pairs ordered pair 1, 1 and ordered pair 2, 2 on the same set A is both symmetric and antisymmetric. The property of transitivity can also be expressed in terms of the composition of relations. Recall that for a relation R on a set A we defined R square is equal to R composition R and more generally R raised to n is equal to R raised to n minus 1 composition R. Then it can be shown that a relation R is transitive if and only if R raised to n is a subset of R for every n greater than or equal to 1. Theorem 1. Suppose C is a collection of relations S on a set A and let T be the intersection of the relations S, that is T is equal to the intersection of all S such that S belongs to C. Then we have the following. A. If every S is symmetric then T is symmetric. B. If every S is transitive then T is transitive. Proof. A. To show that T is symmetric we have to show that ordered pair AB belongs to T implies ordered pair BA belongs to T. For this, suppose ordered pair AB belongs to T. then ordered pair AB belongs to S for every S. Since each S is symmetric, ordered pair BA belongs to S for every S. Hence, ordered pair BA belongs to intersection of all S such that S belongs to C. That is, ordered pair BA belongs to T and T is symmetric. B. To show that T is transitive, we have to show that ordered pair AB belongs to T and ordered pair BC belongs to T implies ordered pair AC belongs to T. Suppose ordered pair AB and ordered pair BC belongs to T. Then ordered pair AB and ordered pair BC belong to S for every S. Since each S is transitive, ordered pair AC belongs to S for every S. Hence, ordered pair AC belongs to intersection of all S such that S belongs to C. That is, ordered pair AC belongs to T and T is transitive. Closure properties. Let P denote a property of relations on a set A such as being symmetric or transitive. A relation on A with property P will be called a P relation. Now let R be a given relation on A with or without property P. The P closure of R written P of R is a relation on A containing R such that R subset of P of R subset of S for any other P relation S containing R. Remark, clearly R is equal to P of R if R itself has property P. The reflexive, symmetric and transitive closures of a relation R will be denoted respectively by reflexive of R, symmetric of R, transitive of R. Reflexive and symmetric closures. The next theorem tells us how to easily obtain the reflexive and symmetric closures of a relation. Note that delta suffix A is the set consisting of all the ordered pairs, ordered pair AA where A belongs to A is the diagonal or equality relation on A. Theorem 2. Let R be a relation on a set A. Then 1. R union delta suffix A is the reflexive closure of R. 2. R union R inverse is the symmetric closure of R. In other words, reflexive of R is obtained by simply adding to R those elements ordered pair AA in the diagonal which do not already belong to R, and symmetric of R is obtained by adding to R all pairs ordered pair BA where ordered pair AB belongs to R. Example 2. Consider the following relation R on the set A consisting of 1, 2, 3 and 4. R is the set of all ordered pairs, ordered pair 1, 1, ordered pair 1, 3, ordered pair 2, 4, ordered pair 3, 1, ordered pair 3, 3 and ordered pair 4, 3. Reflexive R is equal to R union the set consisting of ordered pair 2, 2 and ordered pair 4, 4. That is equal to the set of all ordered pairs, ordered pair 1, 1, ordered pair 1, 3, ordered pair 2, 2, ordered pair 2, 4, ordered pair 3, 1, ordered pair 3, 3, ordered pair 4, 3 and ordered pair 4, 4. And symmetric of R is equal to R union the set consisting of ordered pairs, ordered pair 4, 2 and ordered pair 3, 4. That is equal to the set consisting of the ordered pairs, ordered pair 1, 1, ordered pair 1, 3, ordered pair 2, 4, ordered pair 3, 1, ordered pair 3, 3, ordered pair 3, 4, ordered pair 4, 2 and ordered pair 4, 3. Transitive closure. Definition. Let R be a relation on a set A. Recall that R square is equal to R composition R and R raised to n is equal to R raised to n minus 1 composition R. We define R star is equal to union of R raised to I where I runs from 1 to infinity. The following theorem applies. Theorem 3. R star is the transitive closure of a relation R. Theorem 4. Let R be a relation on a set A with n elements. Then transitive of R is equal to R union, R square union, etc. union R raised to n. Proof. Suppose A is a finite set with n elements. Using graph theory, it can be shown that R star is equal to R union, R square union, etc. union R raised to n. This completes the proof of the theorem. Remark. Finding transitive of R can take a lot of time when A has a large number of elements. Here we give a simple example where A has only 3 elements. Example 3. Consider the following relation R on A consisting of 1, 2 and 3. R is equal to the set consisting of the ordered pairs, ordered pair 1, 2, ordered pair 2, 3 and ordered pair 3, 3. Then R square is equal to R composition R, that is equal to the set consisting of all ordered pairs, ordered pair 1, 3, ordered pair 2, 3 and ordered pair 3, 3, and R3 is equal to R2 composition R, that is equal to the set of all ordered pairs, ordered pair 1, 3, ordered pair 2, 3, ordered pair 3, 3. Accordingly, transitive of R is equal to R union R square union R cube, that is the set consisting of the ordered pairs, ordered pair 1, 2, ordered pair 1, 3, ordered pair 2, 3 and ordered pair 3, 3. Partitions. Definitions. Let S be a non-empty set. A partition of S is a subdivision of S into non-overlapping non-empty subsets. Precisely, a partition of S is a collection P, the collection AI of non-empty subsets of S such that 1. Each A belongs to S belongs to one of the AI. 2. The sets collection AI are mutually disjoint. That is, if Aa not equal to Aj, then Aa intersection Aj is the empty set. The subsets in a partition are called cells. Thus, A belongs to S belongs to exactly one of the cells. The given figure 1 is a Venn diagram of a partition of the rectangular set S of points into 5 cells A1, A2, A3, A4 and A5. Example 4. Consider the following collection of subsets of S consisting of 1, 2, etc. 8 and 9. P1 is the collection of sets, set consisting of 1, 3 and 5, set consisting of 2 and 6 and set consisting of 4, 8 and 9. P2 is the collection consisting of the sets, set consisting of 1, 3 and 5, set consisting of 2, 4, 6 and 8 and set consisting of 5, 7 and 9. P3 is the collection of sets, set consisting of 1, 3 and 5, set consisting of 2, 4, 6 and 8 and set consisting of 7 and 9. Then P1 is not a partition of S since 7 belongs to S, does not belong to any of the subsets. P2 is not a partition of S since the set consisting of 1, 3 and 5 and the set consisting of 5, 7 and 9 are not disjoint. On the other hand, P3 is a partition of S. Definition: given a partition P is equal to the collection Aa of a set S, any element B belongs to Aa is called a representative of the cell Aa and a subset B of S is called a system representative if B contains exactly one element of each of the cells of P. Example 5. B is equal to the set consisting of 1, 2 and 7 is a system of representatives of the partition P3 in example 4. Another system of representatives for the same partition P3 is B1, that is equal to the set consisting of 3, 4 and 9. Example 6. Let collection A1, A2 etc. Am and collection B1, B2 etc. Bn be partitions of a set X. Show that the collection of sets P, collection of Aa intersection Bj excluding phi is also a partition called the cross partition of X. Solution: observe that we have deleted the empty set phi. Let X belongs to X, then X belongs to AR for some R and to Bs for some S. Hence X belongs to AR intersection Bs. This shows that any X in X is in some set Aa intersection Bj. Hence X is a subset of union of Aa intersection Bj. Already we have union of Aa intersection Bj is a subset of X. Hence union of Aa intersection Bj is equal to X. That is, the union of the Aa intersection Bj is equal to X. Now suppose AR intersection Bs and AR dash intersection Bs dash are not disjoint. Say Y belongs to both sets. Then Y belongs to AR and AR dash. Hence AR is equal to AR dash. Similarly, Y belongs to Bs and Bs dash. Hence Bs is equal to Bs dash. Accordingly, AR intersection Bs is equal to AR dash intersection Bs dash. Thus the cells are mutually disjoint or equal. Accordingly, P is a partition of X. Example 7. Let X be the set consisting of 1, 2, 3, etc. 8 and 9. Find the cross partition P of the following partitions of X. P1 is the collection set consisting of 1, 3, 5, 7 and 9 and the set consisting of 2, 4, 6 and 8, and P2 is the collection consisting of the sets set consisting of 1, 2, 3 and 4, set consisting of 5 and 7 and set consisting of 6, 8 and 9. Solution: intersect each cell in P1 with each cell in P2 omitting empty intersections to obtain P is equal to the collection consisting of the sets set consisting of 1 and 3, set consisting of 5 and 7, set consisting of 9, set consisting of 2 and 4 and set consisting of 8. Example 8. Let f of n k represent the number of partitions of a set S with n elements into k cells for k is equal to 1, 2, etc. up to n. Find a recursion formula for f of n k. Solution: note first that f of n1 is equal to 1 since there is only one way to partition S with n elements into either one cell or n cells. Now suppose that n greater than 1 and 1 less than k less than n. Let B be some distinguished element of S. If singleton set B constitutes a cell, then S minus singleton set B can be partitioned into k minus 1 cells in f of n minus 1 k minus 1 ways. On the other hand, each partition of S minus singleton set B into k cells allows B to be admitted into a cell in k ways. We have thus shown that f of n k is equal to f of n minus 1 k minus 1 plus k times f of n minus 1 k, which is the desired recursion formula. Example 9. Consider the recursion formula in the above example. A. find the solution for n is equal to 1, 2, etc. up to 6 in a form similar to Pascal's triangle. B. Find the number m of partitions of a set with m is equal to 6 elements. Solution. Clearly, without using recursion formula, we have f of 1 1 is equal to 1, f of 2 1 is equal to 1, f of 2 2 is equal to 1, f of 3 1 is equal to 1, and f of 3 3 is equal to 1, and so on. Using the recursion formula, we have f of 3 2 is equal to f of 2 1 plus 2 times f of 2 2, that is equal to 1 plus 2 times 1, that is equal to 3. f of 6 4 is equal to f of 5 3 plus 4 times f of 5 4, that is equal to 25 plus 4 times 10, that is equal to 65, and so on. The triangle is given in figure 2. B. Using row 6 in figure 2, we obtain m is equal to 1 plus 31 plus 90 plus 65 plus 15 plus 1, that is equal to 203. Equivalence relations. Definition. Consider a non-empty set S. A relation R on S is an equivalence relation if R is reflexive, symmetric, and transitive. That is, R is an equivalence relation on S if it has the following three properties. 1. For every A belongs to S, A related to A. 2. If A related to B, then B related to A. 3. If A related to B and B related to C, then A related to C. The general idea behind an equivalence relation is that it is a classification of objects which are in some way alike. In fact, the relation equal to of equality on a set S is an equivalence relation. That is, 1. A is equal to A for every A belongs to S. 2. If A is equal to B, then B is equal to A. 3. If A is equal to B and B is equal to C, then A is equal to C. For this reason, one frequently uses tilde or equivalent to denote an equivalence relation. Example 10. Consider the set L of lines and the set T of triangles in the Euclidean plane. The relation is parallel to or identical to is an equivalence relation on L, and congruence and similarity are equivalence relations on T. Example 11. The classification of animals by species, that is, the relation is of the same species as, is an equivalence relation on the set of animals. Example 12. The relation subset of set inclusion is not an equivalence relation. It is reflexive and transitive, but it is not symmetric, since A subset of B does not imply B subset of A. Example 13. Let m be a fixed positive integer. Two integers A and B are said to be congruent modulo m, written A is congruent to B mod m if m divides A minus B. For example, for m is equal to 4, we have 11 is congruent to 3 mod 4, since 4 divides 11 minus 3, and 22 is congruent to 6 mod 4, since 4 divides 22 minus 6. The relation of congruence modulo m is an equivalence relation. Equivalence relations and partitions. Suppose R is an equivalence relation on a set S. For each A in S, let class A denote the set of all elements of S to which A is related under R. That is, class A is the set of all X such that ordered where Ax belongs to R. We call class A the equivalence class of A in S under R. The collection of all such equivalence classes is denoted by S over R. That is, S over R is the collection of all class A such that A belongs to A. It is called the quotient set of S by R. The fundamental property of an equivalence relation and its quotient set is given in the following theorem. Theorem 5. Let R be an equivalence relation on a set S. Then the quotient set S over R is a partition of S. Proof. Specifically, we have to show that 1. For each A belongs to S, we have A belongs to class A. 2. Class A is equal to class B if and only if ordered where AB belongs to R. 3. If class A not equal to class B, then class A and class B are disjoint. 1. Since R is reflexive, ordered where AA belongs to R for every A belongs to S, and therefore A belongs to class A. 2. Suppose ordered where AB belongs to R. We want to show that class A is equal to class B. Let X belongs to class B, then ordered where Bx belongs to R. But by hypothesis, ordered where AB belongs to R, and so by transitivity, ordered where Ax belongs to R. Accordingly, X belongs to class A. Thus, class B is subset of class A. To prove that class A is subset of class B, we observe that ordered where AB belongs to R implies by symmetry that ordered where BA belongs to R. Then by a similar argument, we obtain class A subset of class B. Consequently, class A is equal to class B. On the other hand, if class A is equal to class B, then by 1, B belongs to class B is equal to class A, hence ordered where AB belongs to R. 3. We have to show that if class A not equal to class B, then class A intersection class B is the empty set. For this we prove the equivalent contrapositive statement. If class A intersection class B not equal to 5, then class A is equal to class B. If class A intersection class B not equal to 5, then there exists an element x belongs to S with x belongs to class A intersection class B. Hence ordered where Ax belongs to R and ordered where Bx belongs to R, and by symmetry ordered where Xb belongs to R. Now ordered where Ax belongs to R and ordered where Xb belongs to R implies by transitivity that ordered where AB belongs to R. Consequently, by 2, class A is equal to class B. The converse of the above theorem is also true, that is theorem 6. Suppose P, the collection AI, is a partition of a set S. Then there is an equivalence relation tilde on S such that the set S over tilde of equivalence classes is the same as the partition P. Proof: for A and B belongs to S, define A related to B if A and B belong to the same cell AK in P. We need to show that the relation is reflexive, symmetric and transitive. 1. Let A belongs to S. Since P is a partition, there exists some AK in P such that A belongs to AK. Hence A related to A. Thus the relation is reflexive. 2. Symmetry follows from the fact that if A and B belongs to AK, then B and A belongs to AK. 3. Suppose A related to B and B related to C. Then A and B belongs to AA and B and C belongs to AJ. Therefore B belongs to AA intersection AJ. Hence AA intersection AJ is not the empty set. Since P is a partition, this shows that AA is equal to AJ. Thus A and C belongs to AA and so A related to C. Thus the relation is transitive. Accordingly, the relation is an equivalence relation on S. Furthermore, class A is the set of all x such that A related to x, that is the set of all x such that x is in the same cell AK as A. Thus the equivalence classes under the relation are the same as the cells in the partition P. We can combine the previous two theorems to get theorem 7. The distinct equivalence classes of an equivalence relation on A provide us with a decomposition of A as a union of mutually disjoint subsets. Conversely, given a decomposition of A as a union of mutually disjoint non-empty subsets, we can define an equivalence relation on A for which these subsets are the distinct equivalence classes. Remark: we see that there is a one-to-one correspondence between the equivalence relations on a set S and the partitions of S. Accordingly, for a given equivalence relation R on a set S, we can talk about a system B of representatives of the quotient set S over R, which would contain exactly one representative from each equivalence class. Example 14. Consider the following relation R on S, the set consisting of 1, 2, 3 and 4, and R is the set of all ordered pairs, ordered pair 1 1, ordered pair 2 2, ordered pair 1 3, ordered pair 3 1, ordered pair 3 3 and ordered pair 4 4. One can show that R is reflexive, symmetric and transitive, that is that R is an equivalence relation. Under the relation R, class 1 is the set consisting of 1 and 3, class 2 is the set consisting of 2 alone, class 3 is the set consisting of 1 and 3 and class 4 is the set consisting of 4 alone. Observe that class 1 is equal to class 3 and that S over R is the set of classes class 1, class 2 and class 4 is a partition of S. One can choose either the set consisting of 1, 2 and 4 or the set consisting of 2, 3 and 4 as a system of representatives of the equivalence classes. Example 15. Let R5 be the relation on the set of integers Z defined by x is congruent to y modulo 5, which reads x is congruent to y modulo 5 and which means that the difference x minus y is divisible by 5. Then R5 is an equivalence relation on Z. There are exactly 5 equivalence classes in the quotient set Z over R5 as follows: A0, the set consisting of etc. minus 10, minus 5, 0, 5, 10, etc. A1, the set consisting of etc. minus 9, minus 4, 1, 6, 11, etc. A2, the set consisting of etc. minus 8, minus 3, 2, 7, 12, etc. A3 is the set etc. minus 7, minus 2, 3, 8, 13, etc. A4 is the set etc. minus 6, minus 1, 4, 9, 14, etc. Observe that any integer x which can be uniquely expressed in the form x is equal to 5q plus r, where 0 less than or equal to r strictly less than 5 is a member of the equivalence class AR, where r is the remainder. As expected, the equivalence classes are disjoint and Z is equal to A0 union A1 union A2 union A3 union A4. This quotient set Z over R5 is usually denoted by Z over 5Z or simply Z5. Usually one chooses the set consisting of 0, 1, 2, 3 and 4 or the set consisting of -2, -1, 0, 1 and 2 as a system of representatives of the equivalence classes. Example 16. Let R be the following equivalence relation on the set A consisting of 1, 2, 3, 4, 5 and 6 and R is the set of all ordered pairs, ordered pair 1, 1, ordered pair 1, 5, ordered pair 2, 2, ordered pair 2, 3, ordered pair 2, 6, ordered pair 3, 2, ordered pair 3, 3, ordered pair 3, 6, ordered pair 4, 4, ordered pair 5, 1, ordered pair 5, 5, ordered pair 6, 2, ordered pair 6, 3 and ordered pair 6, 6. Find the partition of A induced by R, that is find the equivalence classes of R. Solution. Those elements related to 1 are 1 and 5, hence class 1 is the set consisting of 1 and 5. We pick an element which does not belong to class 1, say 2. Those elements related to 2 are 2, 3 and 6 and hence class 2 is the set consisting of 2, 3 and 6. The only element which does not belong to class 1 or class 2 is 4. The only element related to 4 is 4. Thus, class 4 is the singleton set 4. Accordingly, the collection of sets, the set consisting of 1 and 5, the set consisting of 2, 3 and 6, the set consisting of 4 alone is the partition of A induced by R. 1. Consider the following 5 relations. 1. Relation less than or equal to on the set Z of integers. 2. Set inclusion subset of on a collection C of sets. 3. Relation perpendicular on the set L of lines in the plane. 4. Relation parallel on the set L of lines in the plane. 5. Relation is parallel to or equal to on the set L of lines in the plane. 6. Relation of divisibility on the set P of positive integers. Note that x divides y if there exists Z such that xz is equal to y. In this unit, we have discussed various types of relations. See you next time. Until then, goodbye.